So we need it to be the case that the judgments we make in English about the truth values of the sentences to which we apply these connecting particles like not, and, or, if then and only if and only if. We need a correspondence between those judgments and the judgments that we make based on the truth table definitions of the truth functions. And the reason why has to do with what the point of logic is. The point of logic is to show that arguments, which we initially formulate in some natural language like English, are valid or not. And so, if the judgments we make in logic concerning the truth functions are different from the judgments about the truth values we make in English about those truth functions, then we would have no reason to think that in logic we were showing valid the arguments in English because of the discrepancy in the truth judgments about truth values. So we need those judgments in English and in logic to correspond perfectly, because if they don't, we're out of business. We are no longer, if they don't correspond, we're no longer looking at whether arguments in English are valid. We're looking at whether arguments defined totally in logic with no regard to English whatsoever are valid or not. And that's meaningless, because the whole point of logic is to show that arguments in a natural language are valid. Anyway, we looked at the definition of the squiggle last week, which is very simple. Since the squiggle just applies to one thing, there are just two possibilities. A sentence is true and it becomes false when squiggled, or a sentence is false and becomes true when squiggled. But now, tonight, we're going to look at the other four truth functions, and we will see that we have to consider four possibilities, because we have two truth values and two atomic sentences connected by a truth function. So and connects something on the left and something on the right. So if you have two truth values and two atomic sentences, that's 2 to the power 2, where the power represents the number of distinct atomic sentences and 2 represents the two truth values. So 2 squared is 4, so there are 4 possibilities we have to take into account when we precisely define the other 4 truth functions. So let's do that. So we'll look at the squiggle, we'll look at the dot, which is the analog of and there's 4 possibilities. They both can be true. The first one can be true and the second one false, or the first one false and the second one true, or they're both false. Okay, and the column underneath the dot will tell us the truth value of this compound sentence P dot Q, based on the truth values of the component truth values for P and Q. So let's think about English. If both P and Q are true, is P dot Q true? Yeah, that's exactly the way we use it. So we want to put a T there. And if any one of these components is false, the whole thing is false. That's the way it happens in English, right? Well, English is spoken in almost every place in the world except Washington, D.C. So, but that's an aberration, a Russian-induced aberration. Okay, So those truth values in the column underneath the dot tell us the truth value of P dot Q. And everything is nice. The book does not worry about this. It says there's a perfect correspondence between the definition in terms of this truth table of dot and our judgments in English about the truth values of sentences that we combine using the particle and. And that's it, if you read the book and do nothing else. But in fact, there are some issues. For one, and can be used additively in English. So here's an example. Some of us are overweight, but not, we don't have a medical problem. Some people have medical problems, and they're overweight by several hundred pounds. I'm talking about someone who weighs like 1,300 or 1,400 pounds, which is a medical problem. Has anyone ever seen someone who's 1,300 or 1,400 pounds? Their lifespans are very short. They could not get into this room. They couldn't fit through the door. It's a terrible problem. It's a disease. But at any rate, suppose you say that this person, Jack, who weighs 1,400 pounds, is as big as a bear and a hippopotamus. And you're incredulous. You say nobody could be that big. So you say he's only as big as a bear. And you say no, false. And then the person says he's only as big as a hippopotamus. You say no, false. And then he says, you mean he's as big as a bear and a hippopotamus? And you say true. So what you've done is used and additively to add together the weights of the hippopotamus and the bear. And that can't be accommodated in the truth table for P dot Q, because if the two component sentences P and Q are false, P dot Q is false. But when you say as big as a bear and a hippopotamus, it's false if it's just as big as a bear, false if it's just as big as a hippopotamus, but true when it's big as a bear and a hippopotamus. You can also use and to indicate a temporal sequence of events. Jack hit the little old grandma and drove on, versus Jack drove on and hit the little old grandma. They are two different temporal sequences, and they have different causal relations. And that can't be captured in this. So everything isn't completely nice with and, but the book says don't worry about it. Well, the book doesn't even talk about this. The book simply says everything's good with and. With or, there's a big problem, which the book notes and I'll talk about. But first let's look at or, which is the wedge and let's look at the last row. If you say something using or, and both P and Q are false, you've said something false. And if you say P or Q, and one but not both are true, you've still said something true in English. But now comes the problem with the first row. There are uses of the word or in English under which it's meaningless to say P or Q when both P and Q are true. The Yankees or the Red Sox will win. The Yankees will win and the Red Sox will win when they play one another. That's meaningless. On the other hand, you can use or in such a way that both P and Q can be true. After class tonight, I'm driving home and getting something to eat. Both can be true, and I still said something true. So, or can be used to talk about mutually exclusive events, both of which cannot be true, in which case you cannot have two T's in the first row of the truth table. You would have to put an F for the truth value of that sentence. But we can also talk about mutually inclusive events, both of which can be true. And so that raises the problem, what's it going to be in the first row, T or F? If it's F, we're talking about mutually exclusive things. And if it's T, we're talking about mutually inclusive things. And both things happen in the world. And it's not like the mutually exclusive things are a tiny, tiny part of what happens. And it's not like the mutually inclusive things are a tiny, tiny part of what happens in the world. You need both. But you can't have it both ways. You can't put T and F in the first row. That's meaningless. To have both T and F right here. That makes no sense. It's either one or the other. And that's mutually exclusive. Okay. You all know from looking in the book that the answer is T. We're just going to accommodate the mutually inclusive things, and we're going to leave out the mutually exclusive things. And that raises a question. What happens when our sentences contain mutually exclusive ors? What are we going to do? You will not find another truth table for the wedge in the book. You will not find two truth tables, one for mutually inclusive or and one for mutually exclusive or. You won't find that. That's one way of solving the problem. Because find mutually exclusive or in terms of mutually inclusive or and two other truth functions, the squiggle and the dot. So if you ever want to translate a sentence in English that uses mutually exclusive or, you can do it by using a combination of mutually inclusive or, the dot, and the squiggle. And it's really simple. The Yankees are playing the Red Sox. The Yankees or the Red Sox will win, but, which we can symbolize by and, but it's not the case that they both will win. That's strange. I wanted to emphasize the darkness, and in fact it erased it, which tells me something's going on with this marker. So the Red Sox or the Yankees will win, but it's not the case that they both will win. And the claim is that this sentence defines the following truth function, which we can call exclusive or. Okay, that's the truth table definition of exclusive, is that this sentence, geez, all these things are starting to disappear. The claim is that this sentence gives you a definition of exclusive or in terms of inclusive or and squiggle. And the only way to verify this is to build a truth table for that sentence. And if, now the dot is the last thing we did in building this sentence. We took P wedge Q and squiggled P dot Q and we dotted them together. So underneath the dot, we should see a column which looks exactly like the column underneath V E, wedge E. But now we have to build a truth table to do that. And so, let's do that. When you build a truth table, you have to fill in underneath every symbol in the with, except the parentheses. You have to put a column underneath every symbol, which means underneath each truth function in the with and each variable or atomic sentence in the with. And you start with the variables or the atomic sentences. Sometimes I'll write a with just variables in it. Sometimes I'll write one with atomic sentences. The one with variables is more general because you can substitute for the variable any with whatsoever, meaning any atomic sentence and any compound sentence. So the first step in building a truth table is to count the number of distinct atomic sentences or distinct variables. How many distinct variables are there in that sentence? 1, 2, 3, or 4? Who says 1? Who says 2? Who says 3? Who says 4? And the correct answer is 2. P and Q. When you repeat P, it doesn't make it distinct. Something distinct from the first occurrence. Spatially distinct, but not distinct as a variable. And then you use the formula 2 to the n, where n represents the number of distinct variables or atomic sentences, to determine how many rows there'll be in your truth table. And there'll be 4. And next, you fill in the columns underneath each variable or each atomic sentence. So that'll be T, T, F, F, T, F, T, F. And that represents the 4 distinct possibilities for the truth values 2 different variables can have given 2 different truth values. Wherever you see P, you repeat that column. So here it is again. So that's T, T, F, F. And Q, here it is again. So that's T, F, T, F. Now, you've got the truth functions to deal with. And that raises the problem. What's the order in which you fill out the columns underneath the truth functions. And the answer is you have to think about the order in which you applied those truth functions to build that width. And the order in which you applied those truth functions to build that width determines the order in which you fill in the columns underneath each of those truth functions. The earlier you used a truth function in building a sentence, that's the order in which you fill in the column. From earliest to latest. The last thing we did was to dot P wedge Q and squiggle P dot Q. So that dot in the middle of that width is the last column that gets filled in. And now here's a question. If this is the last thing that gets filled in, then do we do this first and then this, or this first and then that? And the answer is, if we know the last thing that we do, and it's a truth function that has something on the left and something on the right, then the order in which we precede filling in the dot doesn't matter. We can do anything to the left first and then everything to the right, or everything to the right first and then everything to the left. So if we know the last thing we did, then it doesn't matter for the things to its left and the things to its right, what order we choose. And we can keep going down that way. Let's look at the thing to the right. What's the last thing we did? We squiggled, but there's no other truth functions in here, so there's no worry about order. And over here, there's just one thing. So let's do this one first. And to do this, we just read off that column. T, 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 F. Over here, we squiggled after we did the dot. And those parentheses tell us that. First you dotted P dot Q, and then you squiggled the thing. So that's what we fill in first, the dot, and we just look at that truth table over there. T, F, F, F. And the squiggle reverses that column. So squiggle T is F, squiggle F is T. Okay, and now we are going to dot that width whose truth value is the blue column to this width whose truth value is the first blue column. So T dot F is
F.
loud.
F.
Yeah. T dot T is
T.
T dot T is
T.
F dot T is, and that column is the truth value of this whole sentence, and the column underneath the truth table definition of exclusive or are exactly the same, which proves that that sentence defines exclusive or using inclusive or, the dot, and the squiggle. And that's nice. And that is why you do not see in the textbook two different truth tables for the wedge. One for inclusive or, the other for exclusive or. You don't need it, because you can define exclusive in terms of inclusive. Now that's all the book says. It doesn't go into what would be different if life had been different. Suppose instead of having the truth table for inclusive or in the book, you found the truth table for exclusive or. Then you would have the opposite problem. Given the truth table for exclusive or, how can I define inclusive or? And that's a bonus problem for you if you want to do it. Write a whiff using variables that defines inclusive or in terms of exclusive or. Now, it shouldn't be hard to do, because there are infinitely many whiffs which will do it. Did you want to ask a question? To say it again? Yeah. Write a whiff which defines inclusive or in terms of exclusive or. One way to do it is to think in English about how you would say something if you only had exclusive or, but you wanted to say something which used inclusive or. Or you can just, try some, I've seen some really ingenious whiffs people have written. As I said, there's infinitely many whiffs which will do this. Some of them, though, you don't want to look at, because they're just so wickedly, ridiculously long and complicated.
Can we just do a not?
Can I do a what?
Can we just take the not function of all of them?
But just go over that whiff again a little bit?
Then, yeah.
Okay. So you want the right-hand side?
Yeah.
Okay, so we see squiggle, parenthesized, P dot Q.
Yeah.
And it's the most important one. It's the horseshoe, which represents if-then. And the reason why it is so important is the following. Any argument whatsoever which has that structure, premises, conclusion, any such argument can be rewritten as if P1 and P2, then conclusion. So you can take any argument with this vertical structure and change it into a whiff which has a horizontal structure. So it would look like this: P1 and P2 and horseshoe C. So any argument can be changed into a horseshoe, and then you build the truth table for the horseshoe to determine whether or not the argument is valid. Remember, a loophole to an argument shows the argument is not valid, And a loophole is some situation in which your premises are true and your conclusion false. So if you found an assignment of truth values that made your premises true and your conclusion false, that would be a loophole, and we'd have to put an F here. But you don't know that yet, because what we need to talk about is how we use if-then in English in order to establish what we can say about the truth values for the truth table definition of the horseshoe. So let's take a simple example of an English conditional sentence. Sentences that are if-then sentences are called conditionals, because when you say if-then, you're saying the then part is conditional upon the truth of the if part. Here's a simple example. If you go into the hall right now, you will see someone handing out $1,000 bills. That's my if-then sentence. The first part is you go into the hall. The second part is you will see someone handing out $1,000 bills. So that's if A, then B. Okay, suppose you do go into the hall right now, and suppose you do see someone handing out $1,000 bills. Is that conditional true or false?
True.
True. Suppose you do go out into the hall and there's no one there handing out money. True or false?
False.
So that's simple. If you utter a conditional sentence and the left and the right-hand sides, the if and the then parts are both true, you said something true. If you utter a conditional sentence and the if part is true but the then part is false, then you said something false. But now here's the hard question. Suppose you never go out into the hallway to look. Is it true or false?
True.
Who says true? Who says false? Who says you don't know? This is a problem. If you look in the book, you know what the answer is. It's T. But now, why? How can you say it's true that if you go out into the hall, you will see someone handing out $1,000 bills when you never go out into the hall? The book does not give you an answer that makes any sense. The book does not really understand why you put a T there. However, I can give you an explanation of why there is a T there. Now, it has to do with the point of logic, which is to determine whether arguments in English are valid or not. But there's something I never told you that first night when we talked about validity. And it is the following. If you have an argument in English whose conclusion is always true, the conclusion is a sentence which cannot be false. That argument is valid no matter what premises you have. And if you have an argument whose premises are always false, then that argument is valid no matter what the conclusion. So, if your premises are contradictory, then no matter what the conclusion is, your argument is valid. Here is a valid argument. Premise 1, I am here right now. Premise 2, I am not here right now. Conclusion, tomorrow will be a sunny day. That's a valid argument. And the reason why it is impossible for you to find a loophole to the argument. Remember, a loophole is a situation in which the premises are true and the conclusion is false. But if your premises can never be true, there can never be a loophole. Obviously, it's a stupid argument, and you don't want any part of such arguments, unless you're the president. However, we still need to make room for the judgment that such arguments are valid. And one more thing I can say. Since any argument can be written as a horseshoe, and the column underneath the horseshoe that connects the premises and the conclusion, we can say the truth value of that column is analogous to judgments of validity or invalidity. So if your premises are true and your conclusion true, valid. Premises true, conclusion false, invalid. Premises never true, valid. And that's why you have a T there. If you had an F there, then you would be saying that arguments with premises that can never be true, you would say they're invalid. And that would go against the judgment that they are valid arguments. That's the reason why you have to put an F in rows 3 and 4. The book doesn't tell you that. I once spoke with one of the authors who teaches in New York City, and he said, yeah, you know, you're right. Maybe I should make the change for the book someday. But they never did it. The guy who originally wrote the book is dead. He's been dead like 25 years, Kahane. He died around 1990. But he was the original author of the book, and then it went through a bunch of editions, and the other two guys came in at one point. The book I've used for many, many years. It has a lot of problems. I once went to the publisher to complain about the statement of a certain rule, and it took years for them to change it. It was incorrect in the book. Anyway, let's see. Yeah, I think that's probably enough for the online.